thing. So we have learned why differentiability is important for training the deep architecture. So actually, I mean, in previous lecture, this slide I didn't uh, explain properly. So you have to define this forward rule. We call this kind of thing, I mean, which can, decide the rule that propagate the input x to the y as the forward rule. And inside that f function, there should be some, there is some parameter sector, okay? So this is the forward rule that decide how the input x is processed to output the y, okay? And I mentioned that to be, trained in the deep architecture, the individual layers have to have these two gradient, okay, dy dx, which means the differentiation of output respect to their input, and dy dσ, which means the differentiation of output with respect to the parameter sector, okay. So if these two gradients are defined for individual layer via the chain rule, we can secure the entire deep network also have these two, gradient. So thanks to that, we can get DL dissector, which is the last node, okay? And actually meaning the distance between ground truth and our prediction, which is the L. This is the final node when doing the deep learning. And also we can calculate, we can access all the parameters sector inside the entire deep architecture. And then using this, if we can find this DLD sector, then using the gradient descent formula, we can update them. Okay? So thanks to that, we can train all the parameters inside the deep architecture. Okay. And for some of the layers, for example, pooling or activation layer, we learned last time. They are not having any parameters to learn. Okay, so for that kind of layers, we can only define dy dissector, which is the differentiation of output to the x. Okay, so when getting the DL dissector for entire network, if this individual layer does not have sector, then we can omit that DL sector for this layer because there is no parameter to update. We did not require this DL sector for this layer H. But anyways, this layer had to propagate some signal to the earlier layers, and for that purpose, this dy dx is required. Okay. Anyways, if a network doesn't have any parameters inside, but it has this type of backward rule, which is the differentiation of output respect to that input. If this is defined, then it can be used in the deep architecture. Okay. So any differentiable layers can be used to map arbitrary input to the arbitrary output. Okay, they can be learnable. Okay, but the accuracy can be different. Okay, according to the layers we are using. But for the image domain, the convolution operation that is widely popularly used for processing the image signals. Okay, for example, in Photoshop, we can find a lot of convolutional filter operations to process the image signal. Okay, so and at the same time, this convolution is composed of plus and multiplication, which means their output is combined with this this type of operations, I mean, to connect the input, okay? So every polynomials are differentiable with respect to their input and with respect to their parameters. So this convolution is also differentiable. So they can be used in entire deep architecture, okay? And indeed, when we try to train the overall CNN network using the convolution operation, it is producing good accuracy. So that's why we are using that. And as I told you, the earlier part of the CNN that is composed of mainly convolution operation and also some pooling and activation operation. And later, they are involving fully connected layers, which is same as MLP. Okay, so in the middle, uh, we do flattening. Okay, so flattening means reshaping 2D signals towards the one-dimensional signal. So earlier part, they are continuously applying convolution operation to transform the images. And by doing that, they can somehow extract useful features. And after that, they are mapping 2D, they are reshaping 2D signals to the one-dimensional signal and apply MLPs after that, and this could be interpreted as mapping those features towards the semantic classes. So that is, we call that as classification. Okay, and this is the convolution operation I mentioned. And for image blurring or other types of filtering, we are frequently use 2D convolution operation already. And zero padding was one parameter of the convolution. Okay, and also the stride. This is also important parameter for convolution. So if stride is one, we are, I mean, moving this window. But if this stride is two, then we are moving these windows by 2 pixels. As a result, uh, the output size is reduced. If stride is larger than one, then output size is reduced. Okay. Anyways, but for the zero padding, if it is larger than or equal to one, then the output size is gradually, increased. Okay, so that is the way to control the size of the output given the same input size. Okay. And we also learned about this convolutional layer, and we operate convolutions for given multiple channels of the images by involving several filter. Okay, and then we add them to get the first channel of the output. And by having more filter corners, we can define multiple output channels. So we also can design the channel numbers of the output channel. Okay. Okay, and in PyTorch, this type of convolutions are already implemented. So you can just use this one line of code to implement the convolution operation. Okay. So this is meaning the convolutional layer that have the 3-channeled input and 4-channeled output. Okay, and using the 3x3 corner and zero padding one. And by default, the stride is one. But if you want to use the stride other than one, then you have to specify that as the argument. Okay. And I also told about this pooling operation. Okay, so pooling is meaning picking some value from sub windows. Okay, so this pooling is also designed to reduce the 2-dimension images size. Okay, eventually in classification we have to reduce the 2D signal to the 1-dimensional vector, which is actually the feature. Okay, so pooling is designed for that purpose. Okay, and also at the same time, from these to this, more useful informations are retained. Okay, that is another motivation of having pooling operation inside the deep architecture. Okay. So there are two popularly used pooling operation. One is selecting the maximum value from the sub window. The other is the average pooling that averages the value. But in practice, max pooling is working better than average pooling. So even though it loses many information by choosing this, and they are losing the information from other, non-maximal values, right? But still, max pooling is providing better performance. Okay, so when sampling, when reducing the size of the image from this to this, we will pick the maximum value that is retaining the highest information. Okay. So thanks to that, in practice, the max pooling is working best. Average pooling, it can retain the information from other nearby pixels, right? But still, but in practice, it is not working very well. Okay. So normally we use max pooling, okay? But we also use average pooling. Also, there are some other types of pooling operation as well, okay? And I also explain about these activation layers, okay? So similar to the MLPs, okay? The linear operator, it cannot solely become the nonlinear function, okay? The convolution operation itself is the linear operation because it is composed of plus and multiplication, okay? So in between the linear operation, by explicitly having this type of nonlinear layer or the activation layer, we can give some nonlinearity, okay, into the entire deep architecture, okay? And I also explained the characteristics of these functions before. And so this is the overall CNN architecture. So we are assuming that, we are assuming that the input size is 28 by 28 and having just one channel. Okay. If you want to input the color channel, then you have to assume this is 3. Okay. This is the channel number. And via the first convolutional layer, maybe you want to change it to this dimension. This is the output of their dimension. And then, the dimensions of the responses are becoming like this, okay? Actually, you can design this type of response dimension of the responses by adjusting the output channel number and by adjusting the stride and zero padding. You can control you can control the output channel number directly when making the convolutional 2D operator. And also you can change the dimension of the output by controlling the stride and zero padding. You can anyways decide these responses and control that. And after a while, after applying 5 times convolutions, we will flatten them. And further, we will apply the fully connected layers, and eventually we will map it to 10-dimensional vector. Okay? Every parameters here are randomly initialized. Okay, but we will train this using the data and using the gradient descent algorithm. Okay, are you guys following this? Okay, and I will show you how we can define this complicated architecture. Okay, so previously we just defined net variable using just assigning some linear layer itself for the linear regression, right? Or we can just stack using the sequential function and by stacking multiple linear layers, okay, and nonlinear layers, okay, sequentially and make the MLP layers before, okay. But for the CNN, we can explicitly define the class, okay. So you may learn about this class in maybe data structure, right? So this class can give us the ability to make new instance. Okay, this class is defining some, how to say, the characteristics of our network. Okay, and because you are computer science major, you also remember that I believe you remember this init function, what this init function is. This is the constructor for the class, right? So, I mean, this init is called when this class is first initialized, okay? And never, anyways, it is called when this new instance is initialized. And also, this is some method, okay? This is some method, and here we will define how the input signal X is propagated to generate the final output Y for this network, okay? And actually, there have to be backward function, okay, to find the dy dx, okay? And also there have to be parameter update rule to get this, okay? But we don't have to care about that here because thanks to the PyTorch, if you do not use the PyTorch, you by yourself calculate the closed form solution for this gradient, and you have to implement that here, okay? But as I told you before in the lecture, uh, this gradient calculation could be automatically approximated using some algorithm like Newton's method. Okay, so I mean in the upper class of the this, how to say, the PyTorch, they already implement this backward and parameter update rule by applying those kind of gradient approximation method. Okay, and you never have to re-implement that. Okay, using the same method can be applied regardless of the forward function. Okay, so you don't have to care about this gradient calculation anymore. Okay, but without explicitly implementing that, you may remember that you can call this low stop backward. Okay, because uh, this backward function is already implemented in the upper class. Okay, even though you didn't implement that, they can be called. Okay, so that's why this is the last variable for the architecture, right? So because of that, if you call that, if you call this, every parameters gradients are calculated from the last node, which is the loss function. Okay. Anyways, you can only define the forward function here, okay, because of that. And also, you can only define constructor for the network and how you can only define how to propagate the input to the output. Okay, then the reverse things, calculating the gradient, that can be automatically done in PyTorch. Okay. And this is the example for implementing the CNNs. Okay. We will define two types of layers, okay, which is the convolutional layer first, and second, we will define the fully connected layer. Okay. For the convolutional layer, we sequentially stack multiple convolution operation and nonlinear ReLU convolution again, and pooling and convolution ReLU max pooling. Okay. So this is similar to what we saw in the figure here, right? Are you guys following this? Okay. And you have to uh, calculate this to make them having this type of response dimension. Okay. The only thing you have to carefully design is the response their dimension. Okay. Okay. You have to carefully think about which output, input, and stride padding, those have to be used. Okay. And then you also have to make the fully connected layers. Okay. So we will stack multiple linear, nonlinear, and linear layers after the convolutional layer. Okay. So this will be once called when the instance, the network instance is once called, it once initialized. Okay. And when you first call these functions, all the parameters for the convolution and linear layers will be randomly initialized. Okay. And also, you have to define forward function as well. So this is how we will propagate the input X to output, the final output. Okay, so this is the initial input image. So you will first feed the image input to the self-star layer you define here. This is the convolutional layer, and this is the sorry. This is the intermediate output, okay? And then this is the code for doing the flattening, okay? It is just reshaping the signals, okay? So, I mean, here 7 by 7 by 64 dimensional 2D signals are obtained, and you have to reshape it to 1 by 1 by 1024 dimensional 1D vector, okay? That could be done using this code. And also you will finally apply the fully connected layers, and this becomes 10-dimensional vector, which is the probability vector, okay? So by defining this class, you can you can make the class for the network, the CNN network, okay? And this is the code we just learned, okay? We can define the overall CNN architecture, and we can now make the instance for the network, okay, using the myCNN class we just defined, okay? And these are the code we used for training the linear regressor. Okay, this is the exactly same code we used for linear regressor or training the MLPs. Okay, we have defined the loss function. Here we will use mean square error loss. Okay, calculating the Euclidean distance between prediction and ground truth. And then we will also define the optimizer using the gradient descent. Okay. There are other types of optimizer, and we will further learn after this lecture. Okay. And we have to specify what's the sector and what's the learning rate, epsilon. Okay. So as I told you, the only thing we do not know now, we already know where the parameters, this is sector old, and epsilon, we specify that as 0.01, okay? The only thing we don't know is this, okay? And by the for loop, using this for loop, okay, we first initialize the gradient, this gradient as 0, okay? And then doing the feed forwarding, so inputting the image X to the net we defined here, and it is the 10-dimensional vector, okay, which is the class probability. At initial stage, this is because the net architecture having the random parameter, this output is random, okay? So we will then calculate the loss, which is the distance between prediction and ground truth Y. That is loss, okay? And then by calling this loss stop backward, we can get DL dissector for the entire deep architecture. And by calling this, we calculate this once, okay? And for the empty losses function, we stack we save the loss function that for that iteration. Okay, so we iterated for number of epochs. Okay, so using the same training code, we can train this kind of CNN architectures. Okay, are you guys following this? Okay, without using PyTorch, you can imagine that this type of implementation might be very complicated. Okay, so that's why we are using PyTorch. Okay. Okay. So and also, but this is not enough actually. We have to learn more things actually. So, for example, the first thing we have to learn further is the loss function. So I mean, the final layers of the CNN, as I told you, this is the CNN architecture, this is the input I, and this is the 10-dimensional vector we defined before. Okay, but this 10-dimensional vector cannot be properly trained using the MSE loss. Okay? Uh, this mean square error loss is appropriate loss for regression task. Okay? So if the output is continuous, regression means the supervised learning method. And if the output of the system is continuous, we can, they are called as regression. Okay? But we will train this CNN for the classification task whose output is discrete. Okay? So for that task, this MSE loss is not that proper. Okay, so we will learn about different loss function. Okay. As I told you, this image classification task is assuming that the images, they are having just one main object, okay, and want to classify each image into according to that main object. Okay, so for example, these images are having airplane as the main object, and these images are having automobile as the main object. So we will classify all the images according to their main object. Okay, and also similar for this MNIST data set, they are having 10 classes inside. So they are 0 to 9 containing digits from 0 to 9. So this image will be classified into class 3, okay? And this will be classified into class 0, okay? So there are 10 classes. So this is another form of image classification, okay? These are also other types of benchmark for image classification task. And this is the ImageNet dataset having 1,000 classes, which is the largest image classification benchmark. Okay. Okay. This is you see this graph again. So we saw this from the first lecture. Okay. So we learned about this shallow network already, the BOW combined with SVM. Okay. And uh, we will further learn. Maybe next week we will further learn about this AlexNet, BridgeNet, GoogleNet, ResNet. Okay, we will see which kind of structure they are having. Okay, maybe next week. But before seeing this type of famous CNN architecture, we will see today about the LUNet architecture. Okay, which is in the small scale. Okay, so this LUNet is first proposed in 1980s before the shallow learning period. So that is actually first proposed to tackle this MNIST dataset classification. And for MNIST, it works, but for other types of works, it is not producing very good accuracy. So after this, the researchers are thinking that deep architecture is not very good for multiple generalizable tasks. So that's why they are, developing some shallow learning algorithm. But after this 2012, where AlexNet comes, After that, there was no further issues in deep architecture, and they are actually producing better accuracy compared to the shallow learning. So we are now using deep architecture. Okay. But we will learn about this LUNET maybe today. Okay. But before that, we have to learn, we will learn this LUNET architecture. Okay. So maybe, I'm not sure, maybe next Monday, we will learn about this LUNET. Okay. And maybe the later part of this lecture, I will only introduce this LUNET. But as we learned already, they are composed of uh, multiple convolutional operation in earlier stage. And after that, we are involving fully connected layers, which is MLPs. Okay, after. So their philosophy is same as recent CNN architecture, having convolutions in the earlier part and having fully connected layers at the later part. Okay. This is, I mean, defined early. I don't know. I have to reconfirm this. As far as I know, this is proposed in early 1980s. Okay. But before that, we have to learn about this logistic regression task, and also which kind of loss function is used for classification task first. Okay. For the regression task, as we learned already, we frequently use the MSE loss, which is defined like this. Okay, so we calculate the Euclidean distance between ground truth and our prediction. Okay, and then we want to minimize those Euclidean distance. And another loss we frequently use is this Aaron loss. This is another type of mathematical function that can calculate the distance, continuous distance to argument, right? But we will not use square, okay? But using only absolute values of their distance, okay? Then that is called as error loss. Okay? There are other types of losses also for the regression loss. Okay? If some function can calculate the continuous distance between predicted value and ground truth, we will use that for regression. Okay. And then we will learn about this logistic regression task. This is actually very important, and because they are having similar naming to the linear regression, sometimes we are confused. Okay. Because of same L they are having and same regression they are having. So sometimes this makes it confused, but they are a completely different task. Okay. Linear regression, we are using this type of linear function to make the Y, to learn the W and B parameters, okay, that can best explain X and Y pairs. That's the linear regressor. Logistic regression, we will use similar linear functions. Okay? But after that, we will think something is wrong here. Sorry. After that, after having this type of linear layer, we will apply sigmoid function. Sigmoid. Maybe there should be no minus sign here. Sorry. Okay. The sigmoid function, as I told you before, it is their x range. Their range of x is from minus infinity to infinity, but they can map it having this type of formula. Okay, so if x is inputted, then their y values are confined between these 0 and 1 values. Okay. So after calculating this, applying this linear layer, this output of this linear layer is not bounded, okay, right? We will further apply this sigmoid function on this linear layer's output, okay? Then this output y is now bounded to 0 to 1, okay? Are you guys understanding this? Okay. The thing we want to achieve using this logistic regression is actually, even though their name is regression, we want to do binary classification, which means uh, binary means there are two classes. So using logistic regression, we want to do two-class classification task. Okay, and two-class is 0 and 1. So, I mean, there are two classes whose class is 0 and whose class is 1. And the thing we will do here is we will threshold our output value y. Now, output value y is bounded to 0 and 1, right? And we will threshold our y value to maybe 0.5. If our y is larger than 0.5, we will classify that x sample as 1. And if that x's y value, if we input this x here and check if their value is less than 0.5, we will classify that as 0 class. Okay, this is the binary classification. Okay? Even though our y value is continuous from 0 to 1, it can have continuous values, but we will threshold it and eventually map it to either 0 or 1 class. Okay, are you guys following? Okay, so this is the binary classification. So, I mean, in the sense that two regression tasks, they are somehow using these linear layers in the middle. Okay, but their task is completely different. Logistic regression, linear regression, they are completely different tasks. Linear regression, it wants to do regression using the linear layer, okay? But logistic regression, it actually does binary classification. And it applies nonlinear layers, sigmoid, after the linear layer, okay? Are you guys following this? Okay. And for training the linear regressor, we applied MSE loss. Okay, so by directly close the output of the linear regressor, which is this, to the ground truth y, we use the mean square error loss, calculating the Euclidean distance to the predicted value and ground truth. Okay, but for the logistic regression, for training them, we have to use this type of loss. Okay, they are called as binary cross entropy loss. Okay. This is somewhat different from Euclidean laws because I mean, for the classification task, the final output is discrete, either 0 or 1. We have to use different loss function than the MSE loss. Okay, these two laws are representing the same one. You have to first understand that. Okay. So here, this yn means the GT ground truth class label for n samples. Okay. Okay. This is the binary classification task. It would have either 0 or 1. Okay. And for yn, when one sample's semantic class is 1, then we will apply this loss. We will apply this loss, okay? And for the nth sample whose label is 0, we will apply this loss, okay? That is meant by this formula, okay? And actually here, this is representing the exactly same thing with different formula, okay? So you can first have to understand that. So when yn is equal to 1 for this loss, then when yn is equal to 1, this becomes 0, right? And this term goes to 0, okay? Right? Because if yn is 1, then this becomes 0, and multiplication of 0 becomes 0. So this term entirely goes to 0, okay? And only this term remains, and because yn is 1, this becomes like this, okay? Are you guys agree with this? Okay. So for n samples, we will apply only this LNZN, okay? So that's actually same for this. When n samples label is 1, we will apply minus LNZN for that sample, okay? And also we have to think about what happens when yn is 0, then this goes to 0 because this is 0, becomes 0. This becomes 0, entire term here becomes 0, and only this remain, but this becomes 1. Because yn is 0, this becomes 1, and it become same as actually applying this loss to that nth sample, right? And minus sign is here actually, okay? Are you guys following this? Okay. Actually, the above thing and the below things are same. Okay, you have to understand that first. Okay. And then you have to understand so this is ln gn function. Are you guys on maybe in high school you learned about this log, the graphs for this log function. They look like this, and here is 1,0. When when you input 1 to log function, then their output becomes always 0. This is high school math, actually. And this is the minus ln gn function, okay? We say that when that sample's label yn is equal to 1, which means that sample's ground truth is 1, okay? And Gn means the prediction, okay? We have to close our prediction to the ground truth, okay, Yn. When Yn is ground truth and its value is 1, this Gn should close to 1, right? Are we? And if we apply these laws, okay, and another thing you also have to keep in mind is Gn value, which is the output of sigma of linear function, is bounded to 0 to 1, okay, right? This Gn prediction from the sigmoid of linear function is their values are bounded to 0 to 1, okay? And in this graph, they are lying on this, lying on here, right? Okay. And in this Z range, if you want to minimize this loss, you have to minimize the loss, which is the distance between prediction and ground truth. We always want to minimize the loss, okay? For this Gn, whose label is 1, we are wanting to minimize this, and their minimum is happening here, right? Their y values is minus ln Gn. Their minimum value is here, 0, okay? This is when Gn goes to 0, their loss function is becoming larger and larger, okay? And if Gn becomes close to 1, this is Gn. Gn becomes close to 1, then their loss functions are becoming minimized. Okay. So inversely, you can think by minimizing this, the Gn is becoming close to 1, right? So when Yn is 1, we have to close Gn to the 1. Okay? That is actually achieved by minimizing this loss, ln minus ln Gn. Are you guys understanding this? And the same thing is happening here, okay? When Yn, nth samples, their semantic label is 0, okay? Then we will apply this type of loss, okay? I mean, you can see that also by drawing the same, how to say, graphs like here, okay? If you want to minimize this, that is same as close. That is actually same as making this value goes to 1, okay? Are you guys understanding this? This is 1 minus Gn. X is 1 minus Gn, and this is Y is minus ln 1 minus Gn. If you want to minimize this loss, this 1 minus Gn will go to 1. Then it means this will go to 0. Okay, are you guys understanding this? Okay, so that is actually coincide to our purpose, objective here. So if one sample's class is 1, we want to make our predicted value close to 1, okay? And if that sample's label is 0, then we want to make their predicted value to go close to 0, okay? That can be achieved by applying this loss, okay? Are you guys following this? And this is actually meaning the same thing. Okay? And also in the PyTorch, this binary cross, that is actually, this loss is actually called as the binary cross entropy loss, okay? And this binary cross entropy loss is already implemented in the PyTorch. And as you did for MSE loss, you just can change their name here, loss function's name here, okay? And we will use some iris data set. This is maybe, I'm not sure. If you took the AIP2 course, we already used this iris data to do some classification task. This is having some flower, there are some parameters, having some of the length and width of their some flowers, some dimension. They are having 4 types of such kind of feature, four-dimensional features they are having. They are not having images as input, but having these values, okay? Four-dimensional feature values, which measures their width and height of some flower, okay? And they are having, I'm not exactly knowing, but anyways, 4 types, as far as I remember, 4 types of flower name they are having. So this is actually the classification task, okay? But Mm, I'm not sure. Maybe they are having two types of class. Okay, maybe they are having two types of class. Okay, so this is the logistic regression. Our example should have two classes. Okay, this is what logistic regression does. Okay, logistic regression, they can perform the two-class classification by thresholding their 0 to 1 value, okay? Either having 0 or 1 class. Okay? So from iris dataset I mentioned, we first, get the feature vector, and then also have to get their labels. I'm guessing that this label Y is having just 0 and 1. Okay. And eventually we have to make it as the torch variable. Okay. We have to register in the torch, okay, to let PyTorch to construct the, how to say, the graph structure by connecting the variables. Okay, for that purpose, we have to typecast the NumPy variable into the PyTorch variable. Okay, that's what's happening here. Okay, and we will define linear layer. So as I told, the linear layer we have to have, okay? But we will apply sigmoid function after the linear layer, okay? And our optimizer is gradient descent as before, okay? And this is the same training code, but you can find here, there are one more line, okay? So this is initializing the gradient, and this is calculating this. Okay, our net structure is now just linear layer. Okay, right? And then after that, after getting H, which is the intermediate output, we will further apply sigmoid function for the H. Okay, then that will implement these things. Okay, and that becomes the value from 0 to 1. And we will apply binary cross entropy loss we defined here. Okay, binary cross entropy we defined here by closing our logistic regressor's output with the ground truth 0 or 1. Okay, then loss is calculated, and the loss step backward, we can calculate the gradient for all the parameter, and we'll update that for multiple iterations. Okay. So this is implementing similar, linear regression and logistic regression, seeing the PyTorch code. Even after that, they are very similar, but we are using different loss function and using slightly different structure. Okay. But what they are achieving is quite different. Linear regression, it is doing the regression, okay, using the linear architecture. But logistic regression, it is not using the linear architecture, but using some nonlinear function, okay, by binding their output to the 0, 1 range. And by thresholding that, we want to achieve binary classification. Are you guys understanding this? And this is another similar same. You can also implement this with slightly different way. So this is how to say, binary cross entropy loss with logit inside. So this type of things are already implemented in PyTorch. So you can just implement your architecture as linear here, but your loss is defined. Sorry, your sorry, your loss is defined to automatically apply sigmoid and compare with the, the ground truth. Okay, so this is the ground truth, and our predicted value might be z. So the loss function itself is having applying sigmoid to the output. So that is called as BC with logis loss. But this is kind of implementation issue. So mathematically, there's no difference. Okay. So here, you don't have to apply sigmoid by yourself, but just applying this loss to the output and ground truth, you can train the same logistic regression. Okay. Are you guys understanding this? Okay. So you can, this code is designed to show you for these two different types of loss. You can feel that, if you, their loss functions is indeed providing the same value. I designed this. So if you print out the loss one calculated via this BC loss and loss two calculated via these different types of loss, you can see their loss functions are actually same. Okay. Anyways, this is not that important, but for implementing, you have to also care for this type of things. Okay. And so far, we learned how we can achieve binary classification. Okay. So there is only two classes, 0 and 1. But eventually, for achieving image classification task, we have to perform the multi-class classification. Okay. That is kind of complicated, more complicated compared to the binary classification, and we cannot use this BCE laws on this task. Okay. There are actually two more modules for this. One is the cross entropy laws. This is the generalized version of binary cross entropy laws. So anymore, we don't call these laws with the binary, because binary means there are two classes. Okay. We have to define these cross entropy laws for more than two classes. Okay. And also for the last output, in logistic regression, that's having just one scalar value, but their values are having the values from 0 to 1. Okay, and then we threshold them to get the final class. Okay, but for the multi-class classification, we cannot do that. We cannot do the same thing. Okay? Instead, we have to secure our last output value have to have how to say, number of class dimensional vector. Okay. Okay. If there are 10 classes in the classification task, we are aiming to have 10-dimensional vector that is representing the probability for the 10 classes. Okay. Rather than having this one scalar value. Okay. And for achieving that, we will use this softmax function. Okay. This is not that difficult. Okay. But before learning this, let's think about which kind of characteristic these last responses have to have. Okay, if it can be the probability vector, their sum have to be 1. Is that correct? And also the other condition is their element, each element of this probability vector have to be non-negative. There is no minus probability, right? So each entry of this vector have to be positive, and their sum have to be 1. Okay. This is the condition for the probability, right? And for achieving that, let's say the one dimension, each element of this final output is yi. Yi is the index for each element. Okay. We will, to meet the second condition, we will first apply exponential operator for each element. Okay. So exponential graph looks like this. Okay. So for minus infinity to infinity x value, they will map it to non-negative value. Okay. So by first applying this exponential operator for the last responses, we can secure the second condition first. Okay. And then we will normalize each entry by summing all the entries value. Okay? And we divide each entry with that sum. Okay? And this operation will meet the first condition. Okay? And this is also differentiable operation. I mean, this output is differentiable with respect to y. Okay, and there is no parameter. So this also could be used in the deep architecture. Okay. So I mean, before applying the softmax operation, the final output of network is not constrained. So it can have values larger than 1. Okay. And I mean, can have very large scale values and also can have some negative value. Okay. But after applying the softmax, each entry is secured to be non-negative, and their sum is now error normalized. Okay. And then after applying the softmax, we can call the last output as the probability vector. Okay. And then we will also apply this cross entropy laws to, I mean, make this probability vector mimic the ground truth vector. Okay. I mean, we already learned this binary cross entropy laws. Okay. So if you go to that, they looks like this. These are having ln values. Okay. And this is also having ln values. Okay. So here Q is this P of X is the ground truth. Okay. And PQ is the predicted value. Okay. And this cross entropy loss is by minimizing this cross entropy, we eventually want to make our predicted value Q close to the P, which is the ground truth. Okay. And P of X is one hot encoded vector. Okay. So let's say it's 10-dimensional. If there are 10 classes, then this P of X is a 10-dimensional vector having one for just one element. Okay. There are just one ground truth. Okay. For example, here, the fifth class is the ground truth. So it has one for fifth element and having 0 for remaining ones. Okay. This is the P. And Q is our network's prediction, having some, after the softmax, their sum is anyways 1 and having non-negative values. Okay, so they will have some values that could be regarded as some probability like this. Okay, so we want to make this Q close to the P. Okay, here. But I mean, the extension of this, to say, binary cross entropy laws to the cross entropy, just the cross entropy laws, you can think that as the generalization of these laws to the how to say. So here you can also think that how to say this could be some minus predicted value, and their yn is actually so I mean multiplied here. So this form is actually similar to, you can interpret that similarly to the one term of this cross entropy loss. Okay, are you guys following this? Okay. So I mean, at this stage, I think it would be easier for you to think this as the generalized form of the binary cross entropy. Okay, so actually, the I have to say their form is same as the binary cross entropy loss. Okay, so you can think at this stage same. I mean, this form is actually the generalized form of the binary cross entropy loss. Okay. And another thing, the thing you have to remember is P is the constant. Ground truth is never changed. The thing which is changed is the Q. Okay, we have to change our predicted value, and this depending on the parameters, network parameters, this Q is now changing. And if you simplify this further by how to say this term could be extended using this, right? And this could be simplified by and if you might do it with minus, anyways, I will further. Okay. So using this kind of trick, you can, I mean, make this simple term to the two terms, having two terms, right? So initially, you can involve P of X, okay? It can be ignored, but you are activating those two terms actually and divide them into two terms. And then the eventually we can have this type of two terms, okay? Then you will find that this P of X, because P of X is constant, which is the ground truth, this term entirely becomes the constant term. But the only variable term is the next term. And this is actually mathematically called as the KL divergence, which measures the distance between P and Q. Okay. So this value only be minimized when Px and Qx are same. Okay. So by minimizing how to say this cross entropy loss, because this term is constant, minimizing cross entropy loss is same as minimizing this term, which will have minima when P of X is Q, same as the Q of X. Okay. So by minimizing cross entropy, you can now see these two will become same. Okay. Our prediction Q will be same as the P, ground truth P. Okay. So this is the cross entropy loss we have to use for the multi-class classification. Okay. For the output Q, to close it to the P, which is which is having the one hot encoding, we have to use this cross entropy loss. And also for the last layer of the network, we have to apply the softmax overlay. So the remaining things we will further learn from next Monday. Okay, thank you.